Hi, welcome to tutorial 2, Extended Reality and Smart Immersive Environment. The goal of this tutorial is to introduce the participants to smart immersive environments and to discuss basic ideas and design principles for extended reality applications for IoT-enabled smart built environments. The participants will learn how to incorporate contextualized SBE or smart built environment data, information, and services into extended reality applications, and use the data to improve user interactions with smart immersive environments and provide alternatives for better collaboration among the users, co-located and distributed in smart immersive environments. Several example applications from healthcare and education domains will be presented. And now about the presenters. Hi, my name is Denis Gracanin, and I'm an associate professor in the Department of Computer Science at Virginia Tech. My research interests are at the intersection of human-computer interaction and Internet of Things, including the design of and interaction in smart built environments.
Hello, and welcome to our tutorial. My name is Gracanin. I'm coming from VirBELA Research Center in Vienna, in Austria, and I will be one of the presenters in the tutorial.
The organization of the tutorial is as follows. There will be 4 main parts. Each part will consist of 40 to 50 minutes for presentation and 10 to 20 minutes for question, discussion, and break. And we try to start each part at the top of the hour. We are looking forward to your questions, comments, and suggestions. So the outline of the topics presented include, in part 1, foundations of extended reality and smart built environments, followed by part 2, when we are going to discuss basic idea and principles behind smart immersive environments. In part 3, we are going to talk about user interactions and how to provide affordances for those user interactions, while in part 4, we are going to provide several examples of applications. And that will be followed by a brief conclusion. Hi, welcome to tutorial 2, Extended Reality and Smart Immersive Environment. The goal of this tutorial is to introduce the participants to smart immersive environments and to discuss basic ideas and design principles for extended reality applications for IoT-enabled smart built environments. The participants will learn how to incorporate contextualized SBE or smart built environment data, information, and services into extended reality applications, and use the data to improve user interactions with smart immersive environments and provide alternatives for better collaboration among the users, co-located and distributed in smart immersive environments. Several example applications from healthcare and education domains will be presented. Hi, welcome to tutorial 2, Extended Reality and Smart Immersive Environment. In part 1 of the tutorial, we are going to cover some basic concepts and ideas, and that includes the following. First, we are going to provide an introduction and motivation why smart immersive environments and extended reality are related and why we need to work on that. Then we will talk about basic idea behind extended reality, and then we are going to provide basic description of a smart built environment. So why do we want to do that? What is the motivation? The recent advances in extended reality technologies provide a great opportunity to support deployment and use of extended reality applications in many device domains, because we have also many devices that use spatial mapping to place visual objects in the surrounding smart space, support and building interaction. So therefore, there is a critical mass there in terms of relatively affordable and relatively accurate devices, including various extended reality headsets that can then be used to support necessary capabilities. Rather than just provide virtual environment context of the concept of physical model of the environment, physical environment. So what we have that bridge or mapping between the physical environment and virtual environment. And now the challenge is how to explore various extended reality interaction visualization modalities to identify what are the best practices and how we can bridge that gap between the physical and virtual world. So our goals are to take advantage of affordances and avoid cognition in an extended reality environment. And based on that, or in order to support that, we need a framework that can be used as a testbed for embodied interactive immersive extended reality application. So what is kind of the big picture? When we talk about contextualized data and dealing with physical world, of course we are centered around the subject of user, and that user is placed in the physical world that we can measure through sensors. That user also provides, is a source of information, physiological signals, body tracking, and so on. But also there is a mind, in other words, cognitive load, and that's something that we can get through some user provided information to survey and so on. So therefore, what we then have is that by observing the user in the physical environment through use of sensors and user interfaces, various user interfaces, we can then generate three main streams of data. Firstly, we can have environmental data that includes information such as, let's say, temperature, humidity, or noise level. Then we can also get physiological data in terms of body temperature, heart rate, and so on. And finally, cognitive data, either through some direct input from the user or with some other means. We combine those three streams of data and use them to create stimuli. That stimuli is primarily visual, but it can also include audio and some other types of sensory stimuli. And now that stimuli is being delivered to users in the physical world, and now we are closing the loop. And the whole idea in the behind smart tourism environments is that we can provide that contextualized data to extended reality applications and use them effectively. In order to do that, we can provide services. For example, collecting real-time environmental and physiological data to provide user feedback, analysis of real-time and longitudinal data, and that will allow us to perform some pattern detection, emotion and behavior recognition within a contextual and social context. Because keep in mind also, it is not just a single user. The user is in a built environment where the user interacts with other users, and therefore there is some social component there. In order to do that effectively, what we really want to do, we want to provide support embodied cognition. In other words, understand and record and leverage interplay between brain, body, and world. So how we can implement something like that? Well, first of all, we need to collect and visualize body tracking data, because primary information about user in physical world is where the user is located, what the user is doing in terms of gesture, movement, and so on. Then we also have sensor data, either physical environment or physiological data, and now you can scale it up to multiple sites and physical spaces that are aligned with common extended reality environment. So now we need to organize for mapping between all the data. So therefore, the end result will be support for collaborative interaction. So let's look at foundations of extended reality. First, we can talk about reality-visuality continuum by Milgram and others from 1994, where on one end of the spectrum we have real environment, a physical world. On the other end of the spectrum we have virtual environment or digital world. And then on that spectrum we have various approaches. We have augmented reality, where we augment the real world or real environment with computer-generated object and construct, or we can have augmented virtuality, where we augment virtual environment with video feed from physical world, and anything in between. So therefore, that is the more encompassing concept of mixed reality. But then, when we talk about extended reality, we are really using that as an umbrella term that describes immersive technologies that can merge the physical and virtual worlds. So that includes what you mentioned in the previous slides: augmented reality, virtual reality, and mixed reality, and also other immersive technologies that are being created. All those extended reality devices and systems use, in one way or another, spatial mapping. Why? Because that enables them to place virtual objects in the surrounding smart space and support embodied interaction. In addition to extended reality technology, we are also using other technologies. For example, artificial intelligence to provide non-player character, if you use game terminology, or if you want to provide virtual assistant, or if you want to provide some other information and detect patterns and so on. So that really kind of at the top level. But at the bottom level, we are looking at Internet of Things. In other words, that we have a collection of smart objects that are connected and network together, and that can then exchange information. And when I talk about those smart objects, that can be almost anything that has sufficient computing power, communication capabilities, and sensor that can gather some data and from the environment, and potentially actuators, in other words, affecting that environment. So from that perspective, kitchen appliances or even fixtures can be smart objects, smart lights, smart appliances, and they all provide some kind of services for that. And what we are looking at with smart immersive environments, primarily at the intersection of the extended reality Internet of Things, but also there is a part that on top of that adds artificial intelligence to provide other services. In addition to that, we also need to deal with multi-sensory, multimodal, and multi-scale aspects. We have auditory, vision, haptic, speech, olfactory, sensory information. In terms of modalities for interaction, we have speech, gesture, touch, gaze, body motion, and so on, and also scale for those interactions. And we can look at the in-air gestures that are natural but somehow imprecise. Then we have a micro gesture with better resolution with some additional devices. And then we can also look at the overall motion and fine-tuning interaction. So we can have that multi-scale approach to body tracking at various levels of precision, accuracy, and range. So when we're dealing at that on those various modalities, we can look, for example, at the gaze, where the user is looking, what is the specific point of interest, what is the gesture, for example, hand gesture or perhaps facial gesture to interact with and use interfaces, voice command that provides ability to directly control some interface components or control some actions, And then we can always use a tangible interface, some kind of controller or other smart objects that we can manipulate either through just moving position of that object or by providing some um, special commands or just leveraging interface provided on that tangible object. So therefore, a user interaction then we can look at the head, head pose, where the head is oriented to, facial gestures, speech. Then we can look at the hand through handheld controller using touch, stylus, button, or motion of various devices. But then what really we want to do is to track body. The reason we want to do that because that provides a full body experience. We are able to provide connection between the virtual character and the user. So therefore, rather than having that kind of gap where the user uses mouse or keyboard or some other devices to control virtual character movement, we can look at it as user being quote-unquote that virtual character. For that, again, we need to tracking equipment and the corresponding computational power. Why? Because most of those tracking systems, assuming that they are contactless, are based on computer vision, and therefore that requires processing power, and that's usually done by leveraging sufficiently powerful graphic card. So once we have that, we can provide body tracking as a service. In other words, the body tracking is not directly part of the application. Rather, the body tracking is part of the smart immersive environment, and that smart immersive environment provides that as a service. So what does it mean, or what do we get when we provide the body tracking service? Well, that means that we can then transform physical space. We can look at a simple, let's say, classroom which has some sensor infrastructure, in this case, Kinect version 2 sensor that will provide for body tracking. And by using that service, now we can transform that physical world into mixed reality world where we superimpose computer-generated objects. And the example for that, the training example is nurse training that requires students to practice a number of skills. So let's just observe how it looks like in this video.
Select skill. Next skill.
So again, on this voice command.
Previous skill. Start.
Step 1. Put on clean gloves before handling dentures.
So what we have now, the classroom has been transformed
Step 1A.
into a hospital
Get clean
room.
gloves from the glove box.
The student has to follow a very structured set of instructions and
Step 2.
predefined
Bottom of sink is lined
steps.
or sink is partially filled with water before denture is held over sink. Step 2A. Plug the sink.
Notice that there are no devices. The body is actually used for interactions. So therefore, the user now picks
Step 3.
object
Rinse the
or
denture in
turns on
moderate
the faucet.
temperature running water before brushing them. Step 3A. Pick up the denture. Step 3B. Rinse the denture with streaming water. Step 3C.
And there are various visual tools that help students making sure that washing the denture, for example, in this case, is sufficiently long in order to follow all those requirements for
Step
the
4B. Pick
particular
up the
skill.
toothpaste. Step 4C. Apply toothpaste
So now
to
we
the
can,
toothbrush.
with both hands, we grab the
Step
objects.
4D. Put the toothpaste back into the base.
And as a
Step 5.
consequence
Brush
now,
over
rather
the
than
denture.
students having to go to
Step 5A.
specialized lab
Step 5B.
or
Move the denture
hospital
above the
or
sink.
workstation that can be done in the regular classroom, and to that student can practice steps required for specific skill. And then once that the skill is developed, then of course the final step is to go into actual lab and finalize and get that further improve the experiential learning process. So that was an example how we can actually look at that from the perspective of single user. But we are really also dealing with shared spaces. So an obvious example is what we are doing right now, that we have a shared virtual environment, virtual world, where we have many users, and then those users can then collaborate in certain ways. So we can use keyboard and mouse, but also we can use certain XR devices. And through that, now we can have this tutorial in the virtual world. There are other ways how to do it. Of course, we have Mozilla Hubs, and here is another example for shared learning environment, shared class. What I would like to point out that this is not a new idea. I mean, we had it with SecondLife in roughly a decade ago, around 2010. Again, a lot of push for using SecondLife in education, and similarly, you can move and navigate in that environment, interact by using keyboard and mouse. But it didn't really play out as well as we hoped for, and there are several reasons for that. But in this kind of situation, we have additional motivation, additional reason why we should try it. So first, of course, there is the COVID situation and the necessity to actually use those shared spaces, online collaborative application. The second reason is now that we have devices, extended reality devices, that provide additional ways to interact, not just using mouse and keyboard. Now we can use Oculus device or perhaps HoloLens device, and now we can interact with the space. So the next example will illustrate that how we can connect physical spaces to provide more embodied experience. So this is an attempt, a attempt to connect our two campuses in Blackstone and in Northern Virginia. And what we did, we modeled a virtual classroom based on the actual classroom there. And by providing that room 323 in Falls Church, providing that model, now we have that shared virtual space that we can use to connect various physical spaces. So, of course, due to conditioning assignment, the physical space were basically student apartments or rooms in standard. So what we try to do is to leverage body tracking technology, in this particular case, Microsoft Azure, to use that to provide whole body interaction with the virtual environment. So now as user moves in physical space, it moves in virtual space, and as it moves in virtual space, it interacts with virtual objects and moves them. We have visual cues to actually demonstrate when that interaction takes space. So obviously, there are challenges there because if you are doing that in a space that is cluttered with furniture, etc., body tracking may not be as precise. Also, there are challenges in terms of network connection and so on. So, from that perspective, again, it also depends on implementation. The real challenge is not so much the bandwidth that it is for your connection, but more importantly, what is the latency? What is the delay that you're going to get? Because what you'd like to do, of course, is to have overall latency that is, let's say, 150, maybe 250 milliseconds, and that may actually present a challenge. So in this particular case, we have two participants from two different locations, and they are now in the same shared virtual space. Now, we can then look at that from the perspective point of view of one user looking at the another user, and therefore now you can actually see by using the whole body to navigate in visual space. Now we are reducing or perhaps even almost eliminating the gap between the user and the virtual character in terms of how the virtual character is controlled. In this particular proof of concept, we used IoT protocols because that also allows us to easier integrate Internet of Things infrastructure in those spaces with extended reality applications, but also provide us with the lightweight protocol to exchange critical information, in this particular case, body tracking information. So with that, again, assuming that latency is sufficiently good, we can actually have pretty good results because the bandwidth required is fairly small, in the order of kilobytes per second, or perhaps even less. Another version of this application, example, is using web. So now what we can have is a symmetric interface. In other words, we can provide one location with full body tracking and then use WebGL deployment so that other users can communicate or observe that using web browsing, which we might be doing, let's say, with Mozilla HAUS or similar applications. And therefore, now we can have something that's perhaps well suited for education. The teacher will be in that high-end interface with full body tracking. Students will navigate or use web browser and navigate around and be able to observe what the teacher is doing. In order to support that, of course, standardization is important. We have the standardization on the part of Internet of Things, or we mentioned MQTT and similar protocols that are being used, but also we can use OpenXR, a relatively free open standard that allow us to actually make the software development easier, because we can have an application that can provide support for a number of hardware platforms without the need to rewrite the code, and therefore we also can use it to have that kind of forward compatibility for future devices. So Unreal Engine, Unity, like Blender, engines and development tools, and also HoloLens 2 and Oculus, in terms of XR extended reality devices, are examples of a product that support that OpenXR standard. So now, with that being said, let's now move to foundations of smart built environments. So we covered extended reality. So now, how that plays from the smart built environment side. So what are smart built environments? When we talk about what is going on in built environments, basically houses, apartments, public, buildings, and so on, is that we are having a combination of a physical and social structure. So those structures within built environment change based on the dynamic or activities that are going on, and therefore users in such environment will perform tasks by interacting with smart built environment by viewing and analyzing data that the smart built environment provides. So that provides with various opportunities, having customized and adaptive user interfaces and interaction in order to improve user performance, and then moving away from that human-computer interaction to human-environment interaction. Now, it's looking at the holy grail of human-computer interaction, disappearing user interface, where space around us is the interface, and also our body is our interaction device. So therefore, the smart built environment needs to support the living ecosystem of services, and for that we need a service framework that will support interaction. So in order to understand it better, let's look what does it mean to create a smart built environment. Here is an example of smart built environments, Virginia Tech Solar House, FutureHAUS, and what the process is. So we have that kind of construction part where you assemble exterior and interior, and then in the exterior and interior you're adding various devices. So now in smart built environments, you have a lot of sensors, a lot of data points, collecting all kinds of information from, again, as we discussed before, environmental data, physiological data, and cognitive data, creating those three data streams. So the FutureHAUS is now a smart built environment, and here we can see the final product. And the design process is actually fairly involved. You can use various extended reality applications to go from physical space to corresponding virtual space, to use mixed reality to explore in one-to-one scale design of the physical space, so the design of that smart house, smart built environment in physical space. But then also you can turn it around and use that to explore an existing physical space using your virtual character as a way to explore it. So when we talk about concept of smart home, we are looking at residences equipped with sensors, networks, and intelligent systems. And that's something that started in the 90s, but yet it failed to take off on a large scale. Well, one of the reasons is, of course, the cost involved, because in order to create smart home, it actually takes a lot of investment, and technology was quite expensive. Of course, now these days the technology is getting more and more affordable, and there are more and more efforts how we can have the smart home by starting with systems such as light, power or energy consumption, entertainment, and so on. So one way to look at that is to say, and I know this is kind of topic for discussion, that a smart home is probably not the best term to describe it, because if you think about smart home, that implies, of course, intelligence, and that also implies that there is a way to measure intelligence of home. So, for example, being able to say that my smart home is smarter than your smart home. And I don't think that's really, at least in my, from my perspective, is that we really need to look at that, not so much about being a smart home, but being an empathetic home. In other words, home or built environments that can observe the user, gather information about the user, detect patterns, and be able to be proactive, provide services to that user. What's also missing in terms of smart home is design, how we can actually design smart built environments. And the effort that we're trying to do is to say, okay, let's see how do we design traditional built environments using some traditional architectural methodology. And in that situation, we really deal with built environment and users' living requirements. But in terms of smart built environment, we add one more dimension, which is associated technology. So now we inject the technology into the design process and see how that modify the overall design process for smart built environment. So in that design process, now we can actually look at the interaction model, we can look at the spatial context and physical environmental data, overall user data, data that comes from smart objects, and then through that we can provide some visualization to user either to design the space or to explore the space. So when we look at that smart built environment design, what we are looking at is first ability to deal with traditional architectural modular components and be able to assemble them together. So here is an example of an application, again, that is in itself also a kind of reality application, but allow us to create a smart built environment by creating visual models, assembling them, and together to create the smart built environment. Once that outline of the smart built architectural outline of the smart built environment is created, what we then can do is to do the walkthrough. In other words, we use this model, put it in scale 1:1 in what physical space. In this case, it was a classroom, and walk through that smart built environment. And what we can then do, we can introduce smart technology, explore interaction, see how that works in activity daily living. In this particular case, it was proof of concept, so certainly there is a lot more work to be done, but basic idea is sound. We use extended reality applications to design smart built environments. In that smart built environment, we can then use it to design user interactions, to explore usability and provide affordances for the user experience. Once that's done, then what we can do, we can actually go on site. In other words, we can put that building at the actual location of in almost proper scale, and so now we can look at that from the point of view of, let's say, landscaping, fitting with the surrounding terrain, and that provides an added value. So as we look at the current trends and what is important with smart built environment, so obviously one of the most important things is energy conservation, how we can build some or provide some services that help conserve energy. For example, automatic turning on and off the lights, reducing heating or cooling in rooms that are not occupied, providing then next step is providing home health care by observing user behavior, perhaps detecting some problems and so on. And providing security and safety monitoring, alarm and things like that. Something that's already there, but we can look at that as a more holistic approach when everything's together, integrated together in a single framework. And so the next type of services, let's say, entertainment and comfort, how we can look at that and provide corresponding lighting, playing music, remembering and individual users' kind of comfort levels, the comfort preferences. So we can use the smart environments for education and also to promote social interactions, either collocated or distributed. So for that to work, we need to provide, as I said before, services and application layer that build on top of those services. We also need to provide edge computing services. In other words, IoT, the amount of data can be rather large. Most of the IoT system out there use cloud services, but you really want to have your smart grid environment to be standalone or with perhaps cloud as backup. So therefore, edge computing, local computing is very important. And then from there, you can then work on user interactions, interfaces, and the overall user experience. Initially, of course, dealing with interfaces such as mobile app or some control panels in various places around the house or apartment. But in general case, we would like to have by using user body. So then we can talk about the service framework that is for smart grid environments that can then also support extended reality application by looking at how it builds from bottom to top. So at the very bottom, we need to have an IoT layer that will include sensors, protocols, actuators, all those devices. If we have a large number of devices, then we need to have a data layer that will provide for data collection and fusion services. And then, because energy consumption is one of the big critical parts of in the smart grid environments, we want to provide some energy analysis, especially in reference to perhaps user behavior. So now, in the configuration layer, we now consider user activities and how we can enable or promote those user activity. And also what we need to then provide a way for user to interact with smart grid environment through that user interface layer. So this layered approach to services means that also we need to provide some service management that provides some basic functionality such as safety, security, privacy, and trust, data mining, context awareness, and then support for collaboration, conflict resolution. Again, the smart grid environment, there is not a single user that there are family, there are between public space, people interact, so therefore we need to provide services for collaboration and conflict resolution. And then we also need to observe user behavior evolution, for example, for aging in place. Perhaps we can detect some problems with, let's say, cognitive decline or some health problem, let's say, change in activities, so on. And of course, our basic house control, something that's on the market already through traditional user interfaces. We also need to think about that there is also a longitudinal data collection, because we are looking at smart grid environments not at a single time point, but rather to its history, evolution. So therefore, that longitudinal data can provide a lot of information about patterns of activity, or also allow us to provide contextual data. So in summary, what we have covered in part one, we have discussed how we can connect extended reality and Internet of Things within a single framework to provide foundation for smart immersive environment. We use standardization using various IoT standards or networking standards, in addition to standards such as OpenXR, to promote and support interoperability, which in turn will make it easier to develop and deploy applications and also devices, and also it will reduce cost and therefore facilitate further adoption of extended reality technology, smart built environments, and therefore promotion of smart immersive environments. In part one of the tutorial, we are going to cover. In part two of the tutorial, we are going to discuss smart immersive environments, and we will go through three components of three topics. First, about integration of extended reality and Internet of Things. Second, how do we go from smart environments to smart immersive environments? And then talk a little bit more about context and embodiment for extended reality through an example. So let's first talk about integration of extended reality and Internet of Things. So to do that, let's provide a more formal definition of Internet of Things. So broadly speaking, the Internet of Things is a system consisting of networks of sensors, actuators, and smart objects whose purpose is to interconnect all things, including everyday and industrial objects, in such a way as to make them intelligent, programmable, and more capable of interacting with humans and each other. So now that we have this definition of Internet of Things, so let's look at what constitutes an IoT or Internet of Things system. So that will be a hybrid of physical devices and services, where Internet connectivity is a form of service and other services are needed to make sure that the system works properly, to provide good experience, meaning that exchange of data, access to data, and computing and processing of the data and reacting to data. So therefore, we can think about device ecosystems and service ecosystem merging together in a single or a hybrid ecosystem that then results in creation of an IoT system. So what is an IoT technology in that case? Well, when we talk about IoT, really at the center of the IoT technology are software-defined products. And why? Because really all added incremental value that comes from IoT comes from transforming data collected by sensors or into useful information. And that useful information covers all kinds of aspects, from security, analytics, to look at the big data, and then also for that we need to look at the standardization and perhaps protocol analysis, what happens at the wire, and then how that impacts all the layers up. So when we are looking at Internet thing layers at a, let's say, very low granularity, we can look at the IoT at the cloud. In other words, we have data centers and external systems. We have all many IoT cloud systems, let's say IBM Watson, Microsoft Azure, to name a few. But then from that cloud, when we go down, we are looking at fog, where we actually are looking at Internet of Things gateways, in other words, edge devices, and that we are looking at how we can collect the data from the underlying IoT system or network, if you wish, and process it or perhaps transfer it to cloud. And then finally, we're looking at the mist layer, that we are dealing directly with embedded systems and sensors locally. So therefore, at that lowest level, at edge level, we are looking at bringing physical world and the digital world together. So for physical world, we have sensing through sensors, and those sensors provide measures that are now being provided to digital world. In digital world, we decide on action, or we act, and that action is represented through actuators that provide certain work or certain physical activity that then impacts the physical world, that then make change the sensor's reading, and then we have that closed loop. So let's talk about sensors. So what sensors devices, they are there to measure physical quantity, and then sensor converts the measurement reading into digital value. And we have all kinds of categories of sensors based on, let's say, whether it's contact, not contact, application area, just to name a few. And also, perhaps the more important issue of types, in other words, what is that sensor measuring? Is it position, location, or tracking, occupancy, simple occupancy, pressure flow, or other kinds of environmental data. When I look at the examples of those sensors, we are really looking at things such as perhaps camera, microphone, fingerprint detector, accelerometer, gyroscope, and here we have example of those devices, and they can range in complexity, data they generate, or physical size, level of programming required, and so on. So we have something fairly simple sensor that provides single analog value, and we just need to process it. Those sensor that is in itself programmable and requires fairly involved low-level programming, usually to using I2C protocol. On the other hand, going from digital world to physical world, we have actuators. So they are complementing sensors because they provide the action usually in response to sensing performed by sensors. So again, we have various categories in terms of what kind of motion that actuator provides, power consumptions, ability to control them, or in also sensors or certain physical activity that then impacts the physical world, that then can change the sensor's reading, and then we have that closed loop. So let's talk about sensors. So what sensors devices, they are there to measure physical quantity, and then sensor converts the measurement reading into digital value. And we have all kinds of categories of sensors based on, let's say, whether it's contact, not contact, application area, just to name a few. And also, perhaps the more important issue of types, in other words, what is that sensor measuring? Is it position, location, or tracking, occupancy, simple occupancy, pressure flow. Or other kinds of environmental data. When I look at the examples of those sensors, we are really looking at things such as perhaps camera, microphone, fingerprint detector, accelerometer, gyroscope. And here we have example of those devices, and they can range in complexity, data they generate, or physical size, level of programming required and so on. So we have something fairly simple sensor that provides a single analog value, and we just need to process it. Those sensor that is in itself programmable and requires fairly involved low-level programming, usually to using I2C protocol. On the other hand, going from digital world to physical world, we have actuators. So they are complementing sensors because they provide the action usually in response to sensing performed by sensors. So again, we have various categories in terms of what kind of motion that the actuator provides, power consumptions, ability to control them or resolution and so on. And then we also look at the various types in terms of how that actuation is triggered or achieved. So again, we have mechanical, electrical, electromagnetic, and so on. Some examples of those actuators include various motors or pumps, even some small vehicles. So again, they range in size, complexity, and power consumption and impact on the physical environment. So now that we're looking at those sensor and action, we talk about smart object. That smart object can have both sensor and actuator, and that smart object is then a building block of IoT. And some of the defining characteristics of that smart object includes what is the processing unit, what is computational power, what is the portfolio or assortment of sensor and actuators attached to In part 2 of the tutorial, we are going to discuss smart immersive environments, and we will go through three components or three topics. First, about integration of extended reality and Internet of Things. Second, how do we go from smart built environments to smart immersive environments? And then talk a little bit more about context and embodiment for extended reality through an example. So let's first talk about integration of extended reality and Internet of Things. So to do that, let's provide a more formal definition of Internet of Things. So broadly speaking, the Internet of Things is a system consisting of networks of sensors, actuators, and smart objects whose purpose is to interconnect all things, including everyday and industrial objects, in such a way as to make them intelligent, programmable, and more capable of interacting with humans and each other. So now that we have this definition of Internet of Things, so let's look at what constitutes an IoT or Internet of Things system. So that will be a hybrid of physical devices and services, where internet connectivity is a form of service and other services are needed to make sure that the system works properly, to provide good experience, meaning that exchange of data, access to data, and computing and processing of the data and reacting to data. So therefore, we can think about device ecosystems and service ecosystem merging together in a single or a hybrid ecosystem that then results in creation of an IoT system. So what is an IoT technology in that case? Well, when we talk about IoT, really at the center of the IoT technology are software-defined products. And why? Because really all added incremental value that comes from IoT comes from transforming data collected by sensors or into useful information. And that useful information covers all kinds of aspects, from security, analytics, to look at the big data, and then also for that we need to look at the standardization and perhaps protocol analysis, what happens at the wire, and then how that impacts all the layers up. So when we are looking at Internet thing layers at let's say very low granularity, we can look at the IoT at the cloud. In other words, we have data centers and external systems. We have all many IoT cloud systems, let's say IBM Watson, Microsoft Azure, to name a few. But then from that cloud, when we go down, we are looking at fog, where we actually are looking at the Internet gateways, in other words, edge devices, and that we are looking at how we can collect the data from the underlying IoT system or network, if you wish, and process it or perhaps transfer it to cloud. And then finally, we're looking at the mist layer that we are dealing directly with embedded systems and sensors locally. So therefore, at that lowest level, at edge level, we are looking at bringing physical world and the digital world together. So for physical world, we have sensing through sensors, and those sensors provide measure that are now being provided to digital world. In digital world, we decide on action or we act, and that action is represented through actuators that provide certain work or certain physical activity that then impacts the physical world, that then can change the sensor's reading, and then we have that closed loop. So let's talk about sensors. So what sensors devices, they are there to measure physical quantity, and then sensor converts the measurement reading into digital value. And we have all kinds of categories of sensors based on, let's say, whether it's contact, not contact, application area, just to name a few. And also, perhaps in more important issue types, in other words, what is the sensor measuring? Is it position, location, or tracking, occupancy, simple occupancy, pressure flow, or other kinds of environmental data. When you look at the examples of those sensors, we are really looking at things such as perhaps camera, microphone, fingerprint detector, accelerometer, gyroscope, and here we have example of those devices, and they can range in complexity, data they generate, or physical size, level of programming required, and so on. So we have something fairly simple sensor that provides single analog value, and we just need to process it. Those sensor that is in itself programmable and requires fairly involved low-level programming, usually to using I2C protocol. On the other hand, going from digital world to physical world, we have actuators. So they are complementing sensors because they provide the action usually in response to sensing performed by sensors. So again, we have various categories in terms of what kind of motion that the actuator provides, power consumptions, ability to control them, or resolution, and so on. And then we also look at the various types in terms of how that actuation is triggered or achieved. So again, we have mechanical, electrical, electromagnetic, and so on. Some examples of those actuators include various motors or pumps, even some small vehicles. So again, they range in size, complexity, and power consumption and impact on the physical environment. So now that we're looking at those sensor in action, we talk about smart object. That smart object can have both sensor and actuator. And that smart object is then a building block of IoT. And some of the defining characteristics of that smart object includes what is the processing unit, what is computational power, what is the portfolio or assortment of sensor and actuators attached to or belonging to that object. Communication device, in other words, what kind of bandwidth or protocol is being used. And finally, power source and power consumption, because that can also impact how we use that smart object. So when we look at the smart object, the hardware is an embedded computer or embedded processor that we have our standard perhaps system on chip, which has microprocessor, memory, communication, hardware, and also have some integrated battery charger, general purpose input output that we connect up to sensor and actuators, and then let's say on top of that we have some built-in sensor, for example, capacitive touch support. Now, what we also need to see is that even though we have an object in physical world that is not smart per se, you can still use it in terms of application. So, for example, if you're looking at this microwave here, that microwave can be standalone without ability to communicate. Therefore, it is not a smart object, but we can recognize what that object is, perhaps due to some a computer vision algorithm, or simply by knowing the location, and we have some anchor for that microwave oven, and then we can annotate that and provide information that, you know, where the food goes, how we turn it on and off. So therefore, we can annotate the object in extended reality application and provide some instruction and information how to use. However, more important is ability to actually develop and use smart objects. And that smart object can be perhaps even just a smartphone. Why? Because if you think about smartphone, it certainly has computing and communication capabilities. It does have included sensor devices, let's say accelerometer, but also has the reconfigurable display and touch screen that can be used for input and output. So in this particular example, we are looking at an application where a smartphone is used as a bridge or communication media between the user and participant in the non-player character. So this is an extended reality version of implementation of game theory, various game theory models, where the user plays a game with a computer, and in this case, this is very simple investment and exchange of investing money, getting money back, and through several cycles. So what this smart object then provides is some kind of way to represent interaction in more realistic sense between the user and the computer or represented by this output. So if you look at this example here, so here we have a table and avatar, and then there is a phone user with user interface selecting basic amount of money. So user provides information. The user puts the phone on a certain area on the table that now is being recognized as making an offer. So then avatar picks that phone and then provides the answer to that. And then once that answer is decided, then it actually puts it back, and now user picks it up, gets the information how much was the offer back, and so now that cycle repeats. What we can then do as user does that, we can also measure physiological signal. In this particular case, the user is wearing a particular device to measure electrodermal activity and some other physiological signals. So in this fairly simple example, we can see how such smart object can be used to bridge between user and extended reality application, and by leveraging Internet of Things system and related protocols and capabilities. In more general sense, we are talking about sensor networks when we have a sensor actuator network of SANET, where we have a network of sensors that distribute all across a number of smart objects that sense and measure the environment, and then we also have actuators that act on that environment. Sensor actuators can communicate and cooperate, and we have some examples of that already in smart homes. We have temperature sensors, there are network with air conditioning, and therefore we have that interaction and communication, especially with smart thermostat. How do we deploy that on actual physical device? Well, as we said before, things is a software-defined project. Really, the added value comes from software and application sitting on that smart object. So we have hardware-defined project. Let's say an example of embedded system is Raspberry Pi, but it can be any number of other embedded systems. To that embedded system, we connect a sensor, in this case, sensor measuring temperature. And now we are having a network fabric that has two parts. One is the internal part where we have communication between embedded system and sensor, and then we have external part, and we have IT where we actually communicate between the embedded system and the network and some external system that collects that information. When dealing with IoT, there are several protocols that we use to exchange information between the embedded system and external systems, and arguably the most often used protocol is MQTT, telemetry protocol, which is a lightweight protocol. And so now the question is, well, okay, that's fine. We have the basic idea, but how do we go ahead and perhaps test it and debug it and deploy it before we go about developing the whole application? So there are a number of simulators or modeling tools. This particular example is not red, where we can actually create a whole network of things, put them together using or representing that MQTT protocol. Not only that, the modeling tool can actually integrate actual sensors and also communicate with actual devices that can use that information. So, in addition to modeling, we also want to have some simulation, because you like to be able to predict network performance. Everything is fairly straightforward. We have a couple of things, but if you are going to scale up and have a larger number of things connected together, that network performance becomes critical, because given the network infrastructure, there is a limit to number of messages or the overall bandwidth used by those messages, and that also depends on different protocols. So for that, we have many simulation options and many tools that we can use. So now that we went from its hardware and software aspects to how we model that and real time, and then how we simulate the larger system, then we actually have IoT testers that we can then use them to allow users to see what are the real world performance of the system. So for that, we also need to have some load generators to create messages, to also at the same time provide visualization tools that will allow us to handle that. So then from that we can actually look at what are some issues limiting deployment and even impacting the scope of how we can use IoT. Well, because we don't have a comprehensive end-to-end standards. In other words, from, let's say, sensor on a embedded device to cloud IoT, dealing with cybersecurity solutions and especially when we have like a protocol introduced by using certificates in case of MQTT, and also a relative lack of fully developed vertical application. And if you look at some recent IoT-related conferences, vertical integration is fairly important topic in those conferences. So, and then on top of that, there are some other technical challenges, but also technical opportunities that are faced by the IoT system when used in smart building environments. So now we are going to look at some ways how we can go from those smart building environments to smart immersive environments. But before that, let's just provide a brief overview or explanation of the MQTT protocol that is being used at the IoT level. So that protocol is a published subscriber protocol. So a node that produces data sends message to the broker. That broker then makes a note or has a record what are the subscribers, what are the devices that are interested in data provided by the publisher, and it's the role of the broker to distribute the data to all the subscribers. So when we want to publish some data, the data is associated with topics, so therefore we can have a number of topics, so therefore we can have different publishers for different topics. Subscriber can subscribe to several topics. So again, it is the role of the MQTT broker to effectively, efficiently connect the publisher and subscriber. Okay, so now that we have provided the basic information, let's take a look how we can go from smart built environments to smart immersive environments. So obviously, the next step for that is to take advantage of those low-level IoT protocols and what we just said about MQTT, and use that in connection to devices that we are using for, let's say, tracking, for extended application, and also for display. So now what we are looking at is a device such as HoloLens or any, let's say, similar mixed reality device can be considered or treated as an IoT device. Why? Because it has certain computing power, it certainly has communication capability, it certainly has a lot of sensing capability, and to a certain extent it has actually capability, or at least it is able to provide output to user and provide visual and audio stimuli. So therefore, what we then trying to do is to create an interaction proxy, some framework of services that allow us to connect tracking device such as Kinect sensor to user-side mixed reality headset. So therefore, we are going to have the tracking device publish tracking data to network, or more specifically the MQTT broker, and then we are going to have on the mixed reality headset side, we are going to have tracking client module that will subscribe to the data and send it to the registration model and use it to display. So an example is this telepresence demonstration. And this is an actual demonstration that took place between Virginia Tech and Virginia Military Institute, so between Blacksburg, Virginia and Lexington, Virginia, and roughly 80 miles. And so this was the a local version of that, but in that example that we have this this avatar for a local user being presented to the user in the other side, and overall latency was just for the MQTT messages was roughly 50 milliseconds with added delay for processing. We were under 250 milliseconds, which provided rather nice interactivity. So people were able to, let's say, shake hands with the avatar representation of the user on the other hand. So this is kind of example how we can track user, and the data that you see above is indicates physiological data. The user has an Empatica device left wrist, and it provides information such as temperature in Celsius, galvanic steam resistance, or electrodermal activity, and so on. So that actually provides an additional context in terms of supporting and providing affordances for social interaction. So now, what happens if you want to scale this up? How we can talk about, let's say, general human-IoT interactions and where that leads on a larger scale? Well, first of all, when we talk about human-IoT interaction as a way to support smart immersive environments, it is a two-way interaction. It is a multimodal interaction. It is natural interaction because, again, we want to use embodied interaction, and it is interaction between physical and digital systems. So two paradigms that are emerging these days or recently are Industry 4.0 and Society 5.0 paradigm. And they are, in essence, based on leverage synergy between human-computer interaction and Internet of Things. So, what is Industry 4.0? Well, Industry 4.0 was introduced by German government in 2011, so it is relatively established. And definition of that is cyber physical system production based on heterogeneous data and knowledge integration. And it can be summed up as an interoperable manufacturing process, integrated, adapted, optimized, service-oriented, which is correlated with algorithms, big data, and high technologies such as Internet of Things and services, industrial automation, cybersecurity, cloud computing, or intelligent robotics. So, fairly broad area. It covers a lot of things, but the Industry 4.0 can we also look at the Industry IoT, because what it means that now each of the, let's say, system or device or tool that we have on the factory floor is an IoT device or a collection of IoT devices that generates data. So now when we're looking at that, we can actually get an idea of what is going on. We can have full real-time understanding of the overall manufacturing process, and that information can be provided to users in the context of the actual production environment, as this figure illustrates. So again, that's the industry paradigm. We also have Society 5.0 that provides societal paradigm, and that paradigm was introduced by Japan government in 2016, and they talk about Society 5.0 as a sustainable society for human security and well-being through cyber physical system, or the super smart society that's positioned as the fifth development stage in human society, or in hunter-gatherer, pastoral agrarian, industrial information. So, in other words, that's post-information society. So, if you look at the general outline of that, we see that it does include at the very lowest level embedded devices, sensor actuators that are then through edge computing. The data is then sent to cloud, and in the cloud we have a constant, streaming process. Then we do modeling and mapping. We accumulate data, and then based on accumulated data, we provide services and solution or actuation. In order for that to work, we need to have wide area networking corresponding IoT infrastructure, and then through all that vertical kind of implementation, we need to deal with security, privacy, digital rights protection, and so on. So that kind of conforms what we have discussed previously, just in a very large societal scale. So now that also relates to urban computing and smart cities. So we can also think about using extended reality to interact with or deal with urban computing and interaction with smart cities and services that are provided. So now that we look at how we can go from smart built environments to smart immersive environments and scale it up to paradigms such as Industry 4.0 and Society 5.0, let's talk about context and embodiment for extended reality. And we are going to talk about that through an example. And that's very simple example that has to do with turning on and off lights and light control. When you think about light control, I guess mental model is very simple. We have a single light bulb or single group of light bulbs. We have a switch, and we then turn the switch on and off. And of course, then we can have multiple lights and multiple switches, but that really does not scale up. So let's look at this example. If you are now in a new environment and you see a collection of switches such as this, it will take some time to actually determine which the switch does what, and there is a problem remembering. And so what we really want to do, we would like to actually provide a user interface that will actually allow us to provide with lighting control and based on the context and embodiment. So therefore, a user should have some feedback for their actions, immediate feedback, because these switches may control lights that are not visible from that point of view. And also, think about that you go to some, let's say, building, an office, or let's say some conference hall in a hotel, and if lights are off, first you need to find where the switches are, and then you're dealing with problems to how to control it. So how would we actually address that problem by leveraging context and embodiment? So first, I'm going to provide a couple of demonstrations, and then we are going to discuss what is behind it. So if we are going to move forward and look at next generation smart business environment, also we are going to have a next generation light technology. So now that single source light bulb actually becomes highly controllable and highly granular, linear or even planar light with ability to control intensity or color. So the example that we're showing here is like this. So what we are seeing here is part of the smart house, where we have ceiling, whole surface, and what we have a collection of individual light sources or color lights across the perimeter of that ceiling, and resolution or density of those lights is sufficient that we can actually have very very precise control. So now the question is, what kind of interface we can use? Well, we can always go, let's say, with a mobile app and hit the phone, and it will give us layout of the ceiling. But then the problem is, how is that? How we oriented, and is what we are seeing in our app is well aligned with the ceiling. Instead of that, we can just use body and point to the area we want to light, and use arm gestures to control light. So in this first example, we are going to look at the light control. The idea is that you have one arm to point towards the area where the light should be, and other arm controls the choice of color and intensity. So here, again, in this case, the right arm points to the light, left arm controls color, but then if you switch it, then the left arm can become dominant hand and the right arm can then control. It really depends what was the first arm like. And the way how it was provided is that we have smart immersive environment, and then that immersiveness is not really just because we have extended reality device. It's immersive in the sense that environment itself provides both input and output services, so that the environment provides body tracking services and provides visual display services. So this is the situation with one user, but what happens if we have several users, let's say in this case 2 users? We have that resource sharing, so therefore we need to lock resources. So here is an example of with 2 users, and then you'll see that only one user at a time can actually control. So again, we have first user to the left controlling light, and then when the user is done, second user can then grab control light, bring hand arm up, and then controlling the color there. So what that then becomes is that we can really look at the ceiling as a canvas, and the users are painting on that canvas by setting the individual lights. So what is also important to note is that here that we don't want to overload user with details, how many lights, what is the resolution. It is just the general idea, hey, this is the ceiling has the controllable lights, and you just point, and based on your gesture, we are going to be in the smart user environment will provide corresponding action. So if we look at that, what will be the design goals? Well, we want to have a 3D user interface that should provide basic lighting control tasks. What are those tasks? Selection, sources, turning them on and off, and adjusting color. The user interface should provide users with the feedback. And in this particular case, because we deal directly with lights, it's built in, so to speak. And also, we need to deal with situation with multiple users. Again, I repeat, when we're dealing with smart immersive environments, we should certainly be able to handle one user, but also we always need to think about situations with multiple users and be able to deal with and address potential conflicts and resolve them. So what are the user's actions? So now that we have service that we want to provide or tasks that we want to perform, like light control, what are the possible user actions? So first is claiming control. As we have seen, the user raises a hand, it doesn't matter left or right. Whenever that hand or arm is raised, that becomes the hand that points and determines which light is affected. Releasing control. So now with claiming control, we close the hand, and that gesture is now interpreted as grabbing control. When we open that hand, then we are releasing that control. And all perhaps user body is no longer tracked. User has left the room, or let's say it's for some reason is not visible by the body tracking system. Then we have selection. In other words, the user points the selection head towards light sources. So after the control was claimed, now we can select individual light sources. And then user can switch hands, and then it can do coloring. In other words, the three-dimensional space now becomes this color space. For example, hue, saturation, luminosity, and therefore by using non-dominant hand or non-controlling hand, as we have seen, we can use that to change the color intensity of currently selected light. In terms of architecture, so we actually always respond only to the one user, so we have tracking system knows the geometry of that smart immersive environment. It then does the calculation to determine where the selection hand points to based on the body tracking information, and with coloring hands then I use that to determine color space coordinates, in this particular case hue, luminosity, and saturation. If you look at the architecture side, so again at the center is entity broker, and then user can have both 3D and 2D user interface, so that we can still have that mobile app interacting with entity broker. And then on the actuating side, we have DMX controller that is used to control it. How do we evaluate that? Well, in this particular case, we have 36 individually controllable light LED segments. So we were able to then identify them and provide it to the system. We were able to customize selection tolerance and then have some algorithm determine what is the light source that is actually selected, if we have some overlapping, and also customize granularity of light control, which can also depend on the granularity of possibility to control a light source. Finally, what we also need to consider is some basic system performances. In other words, what is delay? Is it sufficiently fast? And that can be done fairly simple just by doing some recording and looking at when gesture occurs, in this case, close hand in the figure B, and how many frames it takes to have light sync. So now we have from B to F. So we have somewhere between the length of the, let's say, roughly 4 frames of, so which means that 3 to 4 frames. So therefore, we can have the delay between 100 and 167 milliseconds, which is for this particular task modest enough. In summary, what we have covered in this part when talking about smart immersive environments, we discuss how Internet of Things provides a gateway to physical environments of extended reality user. In other words, how we can use IoT to get context and information about physical environment where the user is. So with that, we can then use IoT data to augment extended reality application, and also to provide affordances for user interaction and overall user experience by providing affordances for embodied interaction. In part 3 of the tutorial, we are going to discuss user interactions in smart immersive environments, and we'll do it in 2 parts. First, we are going to talk about context and embodiment for extended reality. We'll revisit some of the points that we discussed in the previous parts. And then we are going to also talk about an example of extended reality interaction in smart immersive environments and study that demonstrates how we can. In part 3 of the tutorial, we are going to discuss user interactions in smart immersive environments, and we'll do it in 2 parts. First, we are going to talk about context and embodiment for extended reality. We'll revisit some of the points that we discussed in the previous parts. And then we are going to also talk about an example of extended reality interaction in smart immersive environments and study that demonstrates how we can compare that with more traditional interaction. So, first about context and embodiment for extended reality. So, when we talk about context, what it means is that we would like to provide or use rich real-time data and put it within situational context. And once you have that, we would like to understand IoT data within that smart built environment context. For example, looking at that from the dimensions of time, location, identity, and activity at the very minimum. So therefore, with that comprehensions of IoT data, we can then try to build synergy or use synergy between smart built environments and extended reality devices to build and provide for that context. As a reminder, let's again see that diagram or figure for contextualized data. What we have user in the physical world. In physical world, we have sensors that collect environmental data and physiological data with the body, and then we have cognitive data, the subject mind, that we can do it from a direct user feedback or input or to some other means, and as a consequence from that physical world and social context, we are getting 3 streams of data: environmental data, physiological data, cognitive data. Those 3 streams of data combine together to provide context, and that context is then used for stimuli creation that is then being delivered back to the user. So now the question is how embodiment fits there. So in terms of embodiment, we need to distinguish different situations when it comes to extended reality application. When dealing with full immersive virtual reality environments, we are talking about situations where users are isolated from the physical world, and as a consequence, that reduces the affordances for embodied interactions. Using that fully immersive VR environment increases the likelihood or percentage of users that experience problems of cyber sickness. In augmented reality or mixed reality environments, we can have sufficient immersion while at the same time also maintaining the affordances for embodied interactions. Why? Because we can see directly the physical world in your place. So therefore, a user has that anchor in the physical world. So the challenge in this situation is how we can identify what are the best practices to leverage embodied interactions and cognition to support extended reality application. And what I would like to emphasize here that immersion alone is not sufficient and must be complemented by embodiment. When we talk about user experience in these situations, we need to remind ourselves that user experience design and human-computer interaction they emerged in the world of desktop computers, and therefore we have corresponding assumptions or approaches. However, that is not being changed by new technology. So now we are talking more and more about user experience for mixed reality applications or in general for extended reality applications. At the same time, also, we need to keep in mind ambient computing and ambient intelligence as its artificial intelligence part, where we are looking at this overall synergy of commodity sensors, connectivity, computing, and analytics that help us redefine the nature of the environment. So we can look at the ambient computing as perhaps a subset of smart grid environments that focus on providing that focus on computing aspects related to ambient in which user is situated. So if you look at some of the definitions that are there, we can look at ambient computing as a convergence of chip sensors, wireless connectivity, increasingly powerful microchips, and advanced analytics. And with that, we can then really redefine the nature of public and private spaces because of the capabilities of services that emerge out of that. So from that perspective, ambient computing provides ambient computing stack and that can serve as a context creation engine that consumes data and then process the data, analyze it, and then process data, result in information that can be used by humans or perhaps some other system in order to provide contextual decision in real time. Emphasis here is that ability to do real-time analytics or real-time computation on the collected data, which then also leads us back to what we discussed about edge computing in IoT. So as we look at that notion of ambient computing that we can find in literature does overlap in terms of description, capabilities, and features with the some aspects of IoT system, and also, as I already mentioned, we can look at it as a subset of smart built environments. So what are the challenges when dealing with user interactions? If you want to design for smart built environment, design with interactions, we need to use some new technology. So now we need to think about, well, how mature is that technology? What is the context of user, or what are the expectations that user have of the system, and how to interact with the system? And so then, which means if you want to perform certain tasks or use certain service, then we may have to use multiple devices, and therefore it may be challenging how to interact with all those devices in order to achieve the task. So when we talk about interaction design, we are really talking about design of device behavior. What we are looking at a sequence of actions between the user and device. And the sequence of actions then allow us to achieve or perform certain action and therefore meet certain goals. So that means that when talking about device, we need to look about, okay, in terms of functionality and functional requirements, what are the user requirements or user-facing function for the devices. So again, focus is on behavior and action. So now that we are looking at that, obviously, we can look at that interaction design as providing a service to a user, and therefore That means that when it comes to service design, we need to have a connected or smart device that provides an ongoing service. So from that perspective, user experience with the service is means that we are looking at the whole lifespan or throughout the activity. So that means that, and also those services evolve over time and are getting refined or changed. So therefore, we need to look at the overall product life cycle that includes not only actual device, but also everything else that goes with that, and as I already mentioned, how those services change over time. So what are the types of interactions? So when we talk about user interactions, what are the types? So first of all, since we are focusing on body interaction, so our bodies and abilities specify or determine how we can talk to devices or provide input. And our sensory system defines output or how we can listen or get information from the devices. So that then leads to embodied interactions, and from that perspective, embodied computing. With new interface technologies that are contactless, or let's say eliminate the need of using traditional user input devices, then we actually have better understanding about user actions and behaviors, because we are directly interacting or observing user rather than having the device as an intermediary. So context-sensitive interaction then can be looked at the circumstances that form the setting for an event, statement, idea, in terms of which it can be fully understood. So therefore, that allows us to enable products to behave or act in ways that are a better match for user routine and behaviors. Also, manage level complexity with little interaction. But then again, we also need to think about the sweet spot, because when dealing with complex systems, let's say smart house or smart built environment, on one end, we can give user full control, which can be very complex with all the settings, all those parameters that need to be set. On the other hand, we can have a system that does, or let's say, determines everything for the user. So giving a recommendation or providing settings. So that's something that can be perceived as patronizing or limiting user control. So between those two extremes, we need to find a sweet spot where, on one hand, user is in control and has ability to change or interact with the environment as need be. At the other, and however, at the same time, is not overwhelmed by the level of detail that is needed to achieve that. One way to deal with that is to provide multimodal interaction. So, because we communicate with world around us using multiple communication channels. So, constant speech, gesture, body language, facial expression, that's an example of communication channel in social interaction. Similarly, when we're talking about interactive device, we can provide, combine different types of interfaces to have a one multimodal interaction. So, putting that all together, we have a number of design considerations. What are the physical controls, if any, that we need to use? What are the available lights and screens in terms of visual aspects? So from audio aspect, what is the audio output, and what are the voice interfaces in terms of input? Then what is the gestural input? What are the capabilities of directly recognizing user movement or gesture? The next is to use objects or props or tangible user interfaces as an intermediary between the user and the system. We can then also, as a part of that, provide tactile output. For example, game controllers provide vibration in certain segments or moments of the gameplay. So with that, we can then think about designing context-sensitive interfaces, especially we then also provide some additional capabilities through computer vision, or maybe some markers such as barcodes, etc., that help us provide better context within the surrounding environment. So what are the physical controls that we can use? Again, switches, buttons, knobs, going back to the example that we've seen before about light control. So that's a typical example of those physical controls and switches. But then, as you also seen there, the problem is what does it mean? So therefore, we need to also show current setting, and that can be expensive to change if you want to redesign the switches or put something else. And we also, when we deal with those physical controls, we have certain expectations or how should I put it, learned skill, how haptic and tactile characteristics of those devices should be, and that also impacts our experience. So what we then want to do if we're going to design a device is how we can integrate physical control within that device. So going back to the example of the smartphone as a smart tangible object, we can provide physical controls or use the touch screen to provide various equivalents to physical controls such as switches or knobs or things like that. So what are the pros and cons or advantages and disadvantages of that? Well, physical controls. Well, it provides direct and fast control. We can have some ability to do some fine adjustment, and if we use it with disability, let's say impaired vision or maybe limited movement capabilities or motoric capabilities, then that can be easier than using, let's say, touchscreen or something like that. However, if you want to do something that can be easily modified, then we can't really change those physical controls without significant investment. If you want to have control from multiple places, then we have those conflicts, and therefore that requires some additional investment or cost or design. So if you look now through individual modalities, so let's first look at the light output. So we have devices that often use lights to show depth, and it can get complicated, and even with a very simple situation, let's say TV and light light indicating status. Another question is, what does it mean when red status light is on? Does it mean that TV is off or TV is on? So, and that has actually changed over time. And then we can also provide some overall stat information so that the light can become main interface. Advantages because it can be easily observed just to take a glance and you know what the information is. However, The downside is that for that we need to use that only when information is comparatively simple. For complex information, our ability to differentiate or effectively use different light information can be an obstacle. So how about visual input? We can use various light sensors to react to ambient lighting condition, using some blink patterns, using QR codes or barcodes, or perhaps some general markers, like in earlier use of augmented reality. So that may require some additional processing to computer vision, but it can also be quite efficient in certain situations. Screens and displays are now fairly cheap, so we can use displays on a number of devices, even very small, very cheap devices have some displays that can be also touchscreen displays that can be used to have dynamic appearance or change of user interface. That allows us to make those products flexible. However, that also means that the user will have to adapt over time. So if you want to keep the user experience simple, using those type of displays can be counterproductive in certain situations. Audio output can be pervasive. In other words, sounds will immediately try visual interactions, so therefore sounds has more impact, at least more emotional impact in terms of communicating the mood of things like that. So therefore, audio output is great for urgent and for time critical alerts because it triggers flashing light without sound is not as effective. But then we don't want to overdo it, and there may be environments where that becomes annoying if you have constant beeping or constant audio indications. Then not only that it becomes annoying, but it's easy. It makes it likely that user will ignore that or won't notice it just because of that being going on often. Voice as output provide a way to directly communicate to user, providing instructions when it comes to, let's say, smoke around some pre-recorded messages or car navigation, GPS, giving us directions or information where to turn, and so that's can be fairly useful, but there are still some usability issues, and choice of tone of voice and support for different languages, and also emotional aspects. So we have that in terms of voice assistants such as Siri or Cortana or similar. So therefore, the way how it should done is that provide ability to customize that, female versus male voice, different versions, and even different accents. On the other hand, using voice as an input leads to speech recognition, and we already have that in devices such as Google Home or Amazon Alexa. The problems are, of course, readability issues, ability to recognize a certain accent, and also ability for that to work in a noisy environment. So what commands are possible, when to listen for a command, and often there is a dependence on the server-side processing, and on top of that, we also have some privacy issues because if such a device has to be constantly on or listen so that it can respond to voice command. That means that arguably that information can be misused or either not necessarily by design, but let's say by omission or by accident. So from that perspective, voice interfaces are good when either channels are occupied, or let's say we are doing something with our hands, and therefore that voice becomes the only available channel for communication. And it allows us to get also provide complex information, but processing that data is challenging because we need to the microphone can read it, get the input, process it, and transfer it into corresponding command. But there is no need for any, or let's put it this way, other than microphone, there is no need for any physical interface. The downside, of course, is a problem with high noise environment, problems with accent or recognition of that, and dealing with international market. The other, another option that we have are gesture interaction, and we already have those with touchscreen, in other words, swiping or pinching, but with advent of computer vision and corresponding sensors such as Kinect or capabilities built into modern extended reality headset, we can use or recognize mid-air gesture. So those are intangible interactions. So, but they can depend on the context, and there is a risk of false positives because we tend to, make gesture all the time as we talk, and therefore we may by accident trigger certain commands. So therefore, using gesture interaction in smart TV environments is good when we have short interaction and when it's clear that gestures are possible. So therefore, it makes sense to limit those gestures in situations where the gesture makes sense. So we had that example for light control. So in that area of living room, raising hand up is probably not likely to happen during normal or regular interaction. So therefore, that can be pretty clear indication that a user wants to control lights. It is not good for precision and length interaction. So what comes to mind is movies such as Minority Report, where they have very sophisticated and very interesting, gesture interaction. However, the problem is if you need to do it for extended period of time, it can be tiring, keeping your arms in the air all the time. And also, if it is not possible to immediately determine that we have false positive, or perhaps the false positive can create a serious problem, by accident, so let's say opening the door or creating noise or something like that. So with that, we have provided an overview of what can happen in terms of interaction. So now we are going to look at a more specific example of extended reality interaction in smart immersive environments. So for that purpose, what we are going to do, we are going to describe a simple user study and some findings that can be interesting and informative. So for some design decisions and for designing more complex and involved user studies. So what we would like to do is not only to evaluate um, user interaction, but also to do comparative study between, let's call it non-traditional, such as mixed reality or gesture-based interaction, and compare it to some commonly based interaction, let's say voice-based and graphical user interface-based. For that, we need to identify certain tasks and then compare those tasks of performance, related performance. And what we have selected here is a set of live control tasks using 4 interaction modalities: MR-based, gesture-based, voice-based, and graphical user interfaces. And what that can help us to understand the usability, learnability, knowability of each modality, and also corresponding scope and limitation. When we are looking at those modalities, again, gesture-based means that we have a body tracking system that can detect gestures. A user does not need any physical device, and feedback is needed because we are controlling lights. Voice-based means that we are using a device such as Google Home to recognize our voice and then send the corresponding commands to lights. Mixed reality based means that we are wearing a headset and we have information or visual overlay that tells us what can be controlled and how it can be controlled. And finally, we can use a graphical user interface that is part of the system provided by light manufacturers. As we talked before, now in smart immersive environment, we want to leverage Internet of Things and make connections with extended reality interactions or interactions in general. So the architecture for that is similar. What we have our foundation or infrastructure, IoT infrastructure that is based on MQTT protocol. We have broker that allow us to connect devices involved, namely the body tracking sensor or Kinect, mixed reality device, namely Microsoft HoloLens, and then a light control system. And that light control system can then be used to control different lights. The overall setup here tells us or shows us how we can identify different lights. In this particular case, we have 4 lights: 2 to the left, 2 to the right, bottom and top. And we can also provide a reference light for comparison, because the reference light provides us with information to use, provides information to user how those 4 lights or one of them should be set up. So let's take a look at the video illustrating mixed reality-based interaction. So here we have a user looking through what can be controlled, selecting light that can be controlled, the corresponding visual indicators appear and allowing user to control that light, going from light to light, changing either intensity or color of the light. So In order to compare all those modalities, we identify 4 light control tasks: turn on, turn off, set brightness, and set color temperature. So we gave to user various assignments, and each of those assignments asked the subject to control and change the state of a randomly selected light bulb to match the state of the reference bulb that we have seen. And that has to be done with one of the 4 supported modalities. And that started from 2 different days in order to complete 3 rounds of assignments. So the first day of session 1, there were 2 rounds, and on the second day, session 2, there was 1 round. Each round had 16 randomly ordered assignments because we have 4 modalities and 4 light control tasks, so 4 by 4 give us 16 assignments. In order to collect data, we used background questionnaire, which has demographic question and questions about subjects' prior experience in using devices or interaction modalities. In terms of post-session, we use system usability scale to evaluate the usability of those 4 modalities, and also we use some quantitative data such as start and finish time, because that can give us the time that it took to complete various assignments. So in our pilot study, we have 10 subjects that are over 18 years old, and here we can see the distribution of demographic information over age, gender, language, education major, and we also have information about skills in using smartphone, using smart speaker or voice-based interaction using Kinect and HoloLens. So from that perspective, we can see that all of them can use smartphone, as expected, and not all of them actually had opportunity to use Alexa or Google Home or some similar device. Kinect, because Kinect is part of the Xbox console, gaming console. We also have 40% of users were able to use it. However, for mixed reality, we had no user that actually had some previous experience. So now what we did, we looked at the learnability. In other words, what was the average task completion time when they actually learn to perform the task. And we can see that the basic tasks, in other words, turn on and turn off, that are kind of binary, that they can be completed fairly quickly. However, setting brightness and color temperature takes more time, just because it is not a binary control. There are multiple levels that need to be set up. We also see here that that especially when it comes to setting color temperature, there is a significant difference between, let's say, a voice-based versus, let's say, graphical user interface based. When we look at memorability, we can then see what is the task completion time. We can now see that the differences are smaller, but there are certain changes and that are perhaps unexpected, because now we are looking at the color temperature, that we actually have changes in terms of which modality performs better. In terms of efficiency, again, we are looking at differences for different types of the tasks, different types of tasks. If you look at the SUS scores, we can see how in session 1 we have 2 rounds. We have ordering, in other words, graph to user interface, highest score, mixed reality, lower score. However, as you look at the session 2, we can see that the gesture improved over voice, so therefore there is something to be said about ability to learn a gesture-based interaction. So also looking at those average score, we can see that from session 1 to session 2, in other words, from day 1 to day 2, the score actually dropped for graph user interface and voice-based. However, it did increase significantly for gesture-based, and it will remain more or less the same for mixed reality modality. So now if you analyze individual modalities for graphical user interface, subjects found that the user interface is fairly convenient, easy to use, although just because of the complexity that the user interface design is a little bit cluttered. And also the challenge was how we can map in the graphical user interface controlling individual light to actual light in the physical world. When it comes to voice-based modality, some subjects found that most convenient, especially for simple commands. However, it became annoying for more complex tasks such as setting brightness or light core temperature. There are of course issues regarding accent or different speed or pausing between the words, and doing that for a prolonged period of time can be annoying or challenging or tiring for subjects. Gesture-based as a modality that is part of smart university environment tend to be most interesting. First, subject found that to be convenient because it doesn't require them to hold the very device, in other words, no need for physical controls. It's also very intuitive. One of the concerns is fatigue, but again, those are the types of the tasks that you don't do often. You don't do it for a prolonged period of time, so therefore occasional control of the light, gesture-based modality is certainly acceptable. Another challenge is, as we mentioned before, is the likelihood of false positives, where system interprets gestures that are not meant to be there. And finally, mixed reality-based, there is some learning curve, learning to how to do air tap gesture, and especially doing that repeatedly. Wearing headset can be problematic, and also not only because of weight and need to but it seems to be redundant to do that for a simple task. But again, the whole purpose is to see, to have something to perform relatively simple tasks that we can use for comparison. However, the positive side of that is that we can use the headset to identify and control smart devices, because while in this particular example, having a light that it's clear from the setup what can be controlled and where those devices are. In general case, when we are not aware what can or cannot be controlled, having visual cues provided by MR modality can be very beneficial. In summary, when we think about the user interaction in smart immersive environment, what is important is to facilitate synergy between smart environments and extended realities devices, especially when providing for context. That can be in two ways. In other words, the data coming from smart environments, that three streams of data can provide contextualized data that can be used in applications, but extended reality devices themselves can provide context to users, as we have seen in this study when mixed reality modality had a visual indicator for controllable light. However, a lot more needs to be done, so we need better understanding of usability and user experience of extended reality when it comes to extended reality, and especially when interacted in and with smart built environments, and therefore being able to better understand what's happening in smart immersive environments. In the conclusion of the tutorial, we would like to reiterate a couple of points. First, a combination of extended reality and smart built environments is possible by using Internet of Things. In the conclusion of the tutorial, we would like to reiterate a couple of points. First, a combination of extended reality and smart built environments is possible by using Internet of Things. In other words, Internet of Things platforms provide integration between physical and digital worlds and support data collections. In other words, for those three data streams that we can use to provide to stimuli to the reader. The Internet of Things can serve as a bridge to applications that can benefit from multiple and heterogeneous data streams generated by SBEs. And those applications require new paradigms for creating user interactions and interfaces in order to take advantage of the available data and thus provide and leverage contextual information, and as well as to use user body as an interaction device with the surrounding environment, thus providing affordances for embodied interaction.
Hello, welcome back to the part 4 of our tutorial.
In the conclusion of the tutorial,
Hello, welcome. Back to the part 4 of our tutorial. In part 4, we will first provide several application examples from immersive analytics to healthcare. Hello, welcome back to the part 4 of our tutorial. In part 4, we will first provide several application examples from immersive analytics to healthcare. Then we will discuss what are the next challenges and opportunities. So let us start with immersive analytics. It is highly related to visualization because we do visual analysis in immersive environment, and visualization deals with supporting humans in extracting valuable information out of large and complex data. In cases where problems are well defined, automatic methods often outperform humans in data analysis. Still, human imagination and expertise is invaluable in cases of complex and ill-defined problems. We need so-called human-in-the-loop solutions there. It means there is a human who steers the analysis, who concludes something based on the numbers and images. Of course, the methods are often combined, automatic and interactive, and by doing so, we take the best from both sides. Procedural computation and huge computing power of computers and machines, and creativity and imagination of humans. One could ask if numbers are not enough. Do we really need images? Do we really need human in the loop? Well, back in 1973, Anscombe asked himself the same question, and he created Anscombe's quartet. It consists of 4 data sets. You can see it here on the screen, set A, B, C, and D. And each of them has 11 items. And interestingly, the numbers are all different, the data sets are different. But if you look at the mean value, the average value of X, for each set is 9.00, for first, for second, for fourth. The mean value of Y is exactly the same on 2 decimal places. Standard deviation for X and Y is exactly the same. Correlation coefficient between X and Y is 0.82, and if you draw a line, linear regression line, so the line that is the closest to the 11 points, for each set, you have exactly the same line. So now, by observing these numbers only, I mean, data and statistics, from data you can hardly imagine how the data set looks like, but statistics might indicate that they are similar. However, if we visualize them using the orange dots here, we see that set A, B, C, and D differ completely. This is an artificial example, just to show you how important it is to see the data. And basically, if you take modern data science and modern data analysis, analysts often, at the very beginning, visualize the data, like we did it now, and they also use visualization to communicate results at the end. Some of them also use visualization in between, because it's much more than inspecting data at the beginning and presenting it at the end. It also very well supports data exploration and analysis. There are many visualization techniques out there. Everyone of us has seen numerous types of visualization. Everyone knows scatter plots, histogram, bar charts, pie charts, dish charts, dead charts. A good visualization differs with respect to data and analysis tasks. You have to know what data is this and then use the appropriate visualization. And what is the analysis task? Why are you visualizing this, what you are visualizing? This is essential to choose a right and good visualization. And there is one technique which is widely used in visual analysis. It's called coordinated multiple views. And we will show it now in a little bit more detail because it's used in many different setups. The main idea is to depict various attributes of data items in more than one view, at least two. And then to allow the user, our human in the loop, our analyst, to select data items in one of the views, and we call this selection brushing. He or she does it interactively with mouse or any other means, but usually with mouse. And then when we select some items in one view, we highlight corresponding data items in all other views, which we call linking. In order to explain it in a little bit more, we created a small video that I will show you now. In this image, you see 4 views. They are very simple. You see 300 points here approximately. These are meteorological stations in California. So we have longitude and latitude here. Aspect ratio is not right, but still you can, if you're familiar with California, you can imagine this is California. We have a Pacific Ocean here. We have here 300 curves that depict temperature, average temperature along a year. So you see here winter time, January until December. You can see that summer is warmer than winters. We have precipitation curve. So there are some places that are quite wet in California in winter, but most of them is dry summer. And we have a histogram of elevation. So we split elevation in 16 bins, and we show how many stations belong to each bin. And we see there are not many high mountains in California. So up to now, it doesn't look very spectacular. So we do have this scatter plot of positions of the stations. We have the curves with temperature. We have the curves with precipitation, and we have a histogram with elevation. Now, let us do brushing. Brushing means I selected some points in one view. So I selected the stations on the Pacific North Coast in California. And then I see in all other views the corresponding data. And this is highlighted in the kind of focus and context visualization so that I see all stations here and my temperatures. And I see stations that I selected are not so hot, not so cold, and they are quite flat. They are quite rainy in the winter, and they have low elevation. Now, I can move the brush along the coast to see what is changing. And you can observe all other views while moving, and you will see these curves do not change much. So obviously, there are some characteristics that closeness to Pacific influences the climate. Now I can select high stations or low stations and see what's going on. See, I have warmer winters. Let us refine the brush. So I introduce another brush here, which says I want low elevation and hot summers. I can see that my stations do not lie on Pacific coast, they're inside. There are few of them in the north and more of them in the south. I can also see that some of them are more rainy and some less rainy in the winter. So I can refine it further. Let us select the ones that are rainy, and they are here in the north and few in the middle. And let us select the ones that are not so rainy. They are in the south. So now we can also change any other brush, not only the last one. So I can say that the second one brush will be very hot places. They are in the south here, as we can see. And of course, I can get quantitative data for my selection. I say show selection, and I see exactly which stations have been selected. So this is something which we call data exploration. So I did not have any hypothesis, but quickly, by spotting some patterns, by brushing, by moving my brushes around, by combining them, I can quickly understand my data and generate some hypotheses. So the question is, can we somehow merge XR and VIS, and how can VIS benefit from XR and vice versa? How could XR offer some new possibilities for VIS? Traditionally, 3D visualization, up to now I showed you only 2D cases, but 3D visualization is used for spatial data. In the right in this slide, here, you can see a visualization of simulation of airflow for revolving door with hot air curtain. So there is a revolving door, it's here, and here hot air curtain is used. So basically the hot air is blown down here so that when door revolves, cold air from outside of the building does not enter the building. And here we show the overall structure of the ridges. Red and blue surfaces depict attracting and repelling Lagrangian coherent structures respectively. We have a large attracting structure in red, this is the hot curtain, and the blue repelling structure. In the left, we see another example of abstract data visualization with coordinated multiple views. You can see clearly we use 2D views here, and we use these complex 3D things here. And in case of spatial data, XR with 3D displays can certainly be beneficial. And this has been recognized a long ago. In this image on the right, you can see two colleagues of mine from Vienna, TU Vienna. Vienna is University of Technology, that use collaborative visualization in augmented reality in 1997. So they visualize some scientific data, and everyone has his own view on it, and they can discuss it. They have see-through glasses, and they can use it. XR it can be also used to depict non-spatial data in a spatial context. Imagine you have some abstract data, but somehow related to some spatial context, to, I don't know, people and their data, and then people are put into the spatial context in a city, for example, and you can combine spatial and non-spatial data visualization. In the next video, in the following video, we will show you how coordinated multiple views have been prototyped in XR for analysis of a fictitious scenario of a power plant incident after an earthquake. Note also voice commands in the XR environment, because in XR we can have more than mouse, which are used to configure the views.
We are displaying here data visualizations of an earthquake event that happened in the city of St. Heimark. This is a time series overview spanning the entire length of the event. To get the details, we are showing data in coordinated 2D views using voice commands such as show histogram. This is a histogram of the user responses for damage reports, and we'll place it on the wall. Next, show scatter plots. The color of the spheres in the scatter plots indicate the magnitude of the data, while the size shows the number of reports sent by the residents. Next, show bar charts.
Okay, this showed you how we implemented the first prototype of multiple views in XR. But again, we had some spatial context. We had this map, which was 2D the input, but it is spatial data. And our final question is, if we have high dimensional data, which is abstract or just in general high dimensional data, can we somehow benefit from XR? One method that is often used in analysis of high dimensional data is nonlinear dimensionality reduction. It means we simplify the data so that we assume that the data of interest lies on an embedded nonlinear manifold within the high dimensional space. If the manifold is of a low enough dimension, the data can be visualized in the low dimensional space. Visualization of such embeddings is very popular today and became a standard way of exploring high dimensional data. Maybe you have heard of multidimensional scaling, MDS, or Disney, just to name these two very widely used methods, which are used to embed data in two-dimensional space, to show them then in 2D space, and to analyze them. But such data, all these embeddings, they can't function 100%, because it's impossible to map high-dimensional data to 2D unless intrinsic dimensionality of data is 2. So if the data in reality, in intrinsic dimensionality is 2, then we can correctly map it to 2D. But most of the data is not. Basically, these methods function because most of the data is relatively low dimensional in its intrinsic dimension. But if it is still in 2D, if we reduce it to too low dimension, to 2D, for example, we will have many false neighbors. So we will have data items that are close to each other in the embedding space, but in reality, they're not close to each other. Or vice versa, we will have points that are far from each other in the embedding, but they are not far from each other in the high dimensional space. And now imagine that we have a high dimensional data of intrinsic dimensionality of 3. We could correctly map it to a 3D embedding and not correctly to 2D embedding. And in this case, XR and 3D can offer a new way for analysis, can be very beneficial. We can explore the 3D embedding in 3D space. So using XR for high dimensional data analysis is still an active area of research. And if you're interested in experimenting with it, we would recommend Immersive Analytics Toolkit, a Unity project to help you build high quality, interactive, and scalable data visualizations in immersive environments. You can download it, you can experiment with it. It's certainly to recommend. Finally, to conclude, I just want to say that immersive analytics bridges with XR and represents a promising research direction. It's very popular at the moment, and while benefits for visualization of spatial data, as well as spatial data, non-spatial data and spatial context are clear, we still need convincing use cases for high-dimensional data visualization XR. We need to carefully consider the benefits from 3D and interaction modalities for abstract data. Conventional methods, displays methods analysis are very advanced at the moment, and XR has to bring some new possibilities. I think it will not be enough to replicate what we have in 2D. We have to find new things that can be done in 3D only. With this, I conclude my presentation here, and Denis will take over from now on. Thank you.
The next application is an immersive gesture-based drone command system. Again, the idea is how to use gesture-based modalities to provide control for comparatively simple task, in this particular case, controlling a drone. So this is the overall architecture where we are using a simulator rather than actual drone. And instead of using conventional controller, we are going to use gesture and display the outcome using Microsoft HoloLens device. And with that, we can then look at some analysis or comparison between conventional RC controller and HoloLens device. To illustrate the basic idea is, here is a short video, so we can see simple gestures in terms of fingers, number of fingers being used to move drone up, then with 2 fingers move drone forward, and then with three fingers actually stopping the drone. So therefore, we can, provided that we have underlying infrastructure, we can relatively simple identify or specify individual gestures and map them to corresponding tasks. When we compare that with that gesture modality with physical control or RC based controls, we can see that for 10 users that were tested, that gesture-based controls perform better because the deviation from the positioning, in other words, each of those users actually had to bring drone as close as possible to the target, that deviation from the target is consistently smaller for gesture-based control compared to the RC-based controls for all 10 users. The next application is using a mixed reality-based system for multimedia content presentation. And that was inspired by traditional architectural student design project presentation that require producing poster and models built from physical materials that can be expensive, or it can produce a lot of waste. So we try to use mixed reality technology to create and present architectural model. So again, the problem that we are trying to address is how to limit material waste during the design and presentation process, and change and adapt traditional architectural design methods to modern technologies. So the basic workflow was to look at what is supposed to be printed poster and create electronic version of that will be not only the actual image of that poster, but also will include 3D model and also audio component. And those posters can then be placed in a physical space. So a simple example of use provides us with many of the posters that are there for this demonstration, just roughly 10 posters. And what we can do, we can start with one poster and then expand to all posters. So museum, combining voice commands. And so now we have poster in place, and now we can look at it, explore it, perhaps change to another poster using different studio topic, and then select the corresponding 3D object, explore it in space, analyze it, and then probably have added functionality compared to traditional poster that will have to have the physical prop nearby, which can be difficult to manage. all. So now with all the posters, they're all spaced around available walls and then corresponding surfaces. So user can walk around and look at it. So you can imagine that each of those students can look at the posters at different physical spaces. So that proved to be rather interesting, and future work will could use some more emphasis on multi-user features, how to better zoom in and zoom out, how to annotate and make comment, integrate the body tracking, and also provide support for mobile devices in addition to extended reality devices. The next application combines Internet of Things, artificial intelligence, and extended reality in a single package, so to speak. So that's the topic is how to actually go towards the real-time object recognition for context awareness, mixed reality, machine learning approach. The system architecture is such that it uses computer vision and corresponding computer device to provide machine learning based object recognition that will identify object and provide corresponding label, which then using again MQTT, as we talk about integration of bridging between Internet of Things and extended reality, will then publish to the broker, and then Microsoft HoloLens device can now subscribe to those levels, to that information, and display corresponding information and instruction. So the particular case study is decorating a Christmas tree. So the notion is that, from every year we want to decorate the tree the same way, and one way to do it is to use mixed reality that will guide us where to put individual decoration. So for that, we are going to use camera and register or identify an object by simply bringing it in front of camera, and we can imagine that it can be integrated throughout the physical space, and therefore we will then be able to specify that in wide range. But again, there is a trade-off. In this particular case, the physical volume where that recognition takes place is fairly small, so therefore the gesture has to be intentional. If we have wider coverage, then it is possible to have false positive and detecting gesture that's really not there. So once that we have registered that, so now in the follow-up example, now we pick another decoration, again register it, and then looking at the, we can see the first decoration that we use. So now we pick both of those, and then we can go to 3 and place those decorations in corresponding places. So red to match red marker, and similarly for the blue decoration, put it in place there. The last example has to do with autism spectrum disorder. It's actually relatively old study, maybe 4 or 5 years, probably 4 years ago. And idea was how we can use this approach to integrate fairly complex physiological data and with body tracking or position tracking, I should say, and with that, provide specific stimuli for, in this particular case, adolescents that are on autism spectrum. So in terms of architecture, what in data that have been collected, we used Empatica to collect basic physiological data such as heart rate, blood pressure, electrodermal activity, and also a wireless EEG cap to record brain activity. So that was put together to provide real-time feedback on accuracy of facial emotion recognition. So what we have created is a sequence of scenarios with various actors performing tasks.
Hello. Abstract aircraft and the ones, and you can see we have used which we visualization techniques. Welcome back to the show with the ones that you imagine that we have a command.
Figures move the radiation from physics, explore it. So, for example, the study maybe 4 or 5 years, probably 4 years ago, and idea was how we can use this approach to integrate fairly complex physiological data and with body tracking or position tracking, I should say, and with that provide specific stimuli for, in this particular case, adolescents that are on autism spectrum. So in terms of architecture, what in data that have been collected, we used Empatica to collect basic physiological data such as heart rate, blood pressure, electrodermal activity, and also a wireless EEG cap to record brain activity. So that was put together to provide real-time feedback on accuracy of facial emotion recognition. So what we have created is a sequence of scenarios with various actors performing tasks, real world, in this particular case, looking for a particular product, looking around, whether there is similar product somewhere else. And again, this is comparatively other examples. So, but the main idea was to provide some kind of situation where users should be able to detect certain emotion. So user received basic feedback about the accuracy of that, and then here again we are going back to similar situation, exploring product before buying it, and then trying to identify emotion of that user. There was a collection of characters with different descriptions, and there are a number of scenarios where that were provided to use. So now with that, we are done with application example, and let's now discuss about what is next for extended reality, what are the possibilities and opportunities. So again, just to remind ourselves, extended reality is an umbrella term for all the immersive technologies, not those that we already know, such as augmented reality, virtual reality, and mixed reality, but also the new immersive technologies that are being created. So some of the challenges that we have just identified when it comes to using extended reality and also in smart immersive environment, data generation, collection, how that scales up, what are the privacy security issue, the cost of that technology, practicality, in other words, especially for certain tasks. We had that example for light control and using an XR device, which obviously is could be an overkill for such a simple task. However, there are interesting opportunities. Just looking at the potential for growth, the worldwide extended reality market is expected to grow 7.7 times between 2018 and 2022. And by 2021, 1 in every 3 small and mid-sized business in the United States is expected to be piloting an extended reality-based training program for employees. So that alone demonstrates a strong interest and potential and need to better explore extended reality. And especially in those training applications, that's something that happens in physical space. So therefore, smart immersive environments are a logical choice for that. Looking at the areas or application domains for extended reality, we can look at education, training, healthcare, entertainment, all the way to building construction, manufacturing, data analytics, and smart cities in general. So just one example of that, education. Why is it important? Because especially in a situation with the distance learning where engagement and knowledge retention is a problem, we can see that from literature that K-12 educators can use extended reality to boost student engagement, and high school, higher education, there is empirical evidence for efficacy. In other words, the efficacy of extended reality technology for teaching and learning and benefits from it. Specifically for global market for extended reality education and training, it will grow from approximately 1 billion in 2018 to between 2 to 10 billions by 2026. Again, a very important application domain and strong potential for growth. In summary, for part 4, extended reality can be used in many domains, ranging from visual analytics to healthcare, and there is certainly tremendous growth potential for extended reality technology and applications. In the conclusion of the tutorial, we would like to reiterate a couple of points. First, a combination of extended In the conclusion of the tutorial, we would like to reiterate a couple of points. First, a combination of extended reality and smart built environments is possible by using Internet of Things. In other words, Internet of Things platforms provide integration between physical and digital worlds and support data collections. In other words, those three data streams that we can use to provide stimuli to the user. Internet of Things can serve as a bridge to applications that can benefit from multiple and heterogeneous data streams generated by SBEs. And those applications require a new paradigm for creative user interactions and interfaces in order to take advantage of the available data and thus provide and leverage contextual information, and as well as to use user body as an interaction device with the surrounding environment, thus providing affordances for embodied interactions. As far as smart immersive environments are concerned, it is important to have to leverage the presence of tangible, reconfigurable smart object because that can provide tremendous opportunities for enhanced interactions. That synergy between extended reality and smart built environments, resulting in smart immersive environment paradigm, provides an infrastructure for context-aware interactions and allow us to develop user interfaces that are augmented with contextualized data visualization. Smart immersive environments allow us or enable us to move away from the egocentric approach where physical devices are mounted on the user body and that's how we get data. Rather, we can then emphasize embodied interactions. Opportunities and challenges that we are facing when dealing with smart immersive environment and extended reality is that we need to look at extended reality devices as IoT devices so that they can be fully integrated. That requires work on communications and data exchange, and also to provide the infrastructure for service discovery, for semantic information ontologies, address scalability challenges, maintain support for security, privacy, trust, and safety, and also think about new ways to provide authoring, developing, and debugging of applications. This work has been partially supported by Virginia Tech Institute for Creativity, Arts, and Technology, and by the VirBELA Research Center that was funded through several grants. At the very end, just very briefly going to the list of references that we have used in these slides. And finally, thank you very much for attending this tutorial. In the conclusion,
Hello, welcome back to the part 4 of our tutorial. In part 4, we will first provide several application examples from immersive analytics to healthcare. Then we will discuss